Hello, this is Mrs. Pullen for AP Statistics, Lesson 6.11, and in this video I'm going to go over how to conduct a two-sided significance test. A state's DMV claims that 60% of teens pass their driver's test on the first attempt. A reporter examines an SRS of the DMV's records for 125 teens. 86 of them passed the test on the first try. Is there convincing evidence at a 5% significance level that the DMV's claim is incorrect? So, when you're asking for convincing evidence, for the most part, we think of performing some sort of hypothesis test or significance test. We're dealing with categorical data, either the teens pass or they don't, so we know we're dealing with proportions. So the first step of this process is to state the parameter, the hypotheses, and the significance level. So the parameter, what you're trying to discover, is the true proportion of teens that pass their driver's test on the first try. And the null hypothesis is what you're assuming to be true. So the DMV is claiming that 60% pass on the first try. The alternative is what you're suspecting to be true. And since this particular scenario doesn't provide a direction, so whether we expect it to be a higher proportion or lower proportion, we do something called a two-sided test. So we say we're looking at the probability that it's just not going to equal to 0.6. And they defined our alpha as 0.05. And it's a good idea, even though it's not mandatory, to write out the statistic, which is p hat 86 over, I'm just entering it in my handheld, 86 divided by 125 is 0.688. Okay. Next, we verify the condition. So again, because it's a not equal, we're going to conduct a two-sided test. So the next thing we're going to do is we're going to write out the conditions. So the first is SRS is stated. The second is it is reasonable to assume that there are more than 1,250 teens who will take a road test. And that's probably a very reasonable assumption. The third condition is that normality condition. And again, when you're dealing with hypothesis tests, since you define P in your null hypothesis, that's what you should be using. So there are 125 times 0.6, and 125 times 0.6 is 75, and that's certainly greater than or equal to 10. And NQ is 125 times 0.4, which is certainly greater than or equal to 10. So I met that condition, and so you need to state the name of the test. That's why we use this line. Since conditions have been met, we can perform a one proportion z-test. Next is the calculations. So we start off by drawing a normal curve, and the mean of this sampling distribution, which can be represented as a normal curve based on satisfying condition 3, is going to be P. It's what we're defining it. Okay. And we got a test statistic of 0.66. So, which is above the mean. However, when you're doing a two-sided test, because you didn't know which direction, you also have to kind of look at that mirror image. So like if you folded it over, like the normal curve over the mean, and we have to figure out what that value would be. So let me just correct this. So this is a difference of 0.066. Wait, hold on. 688. Hold on, I wrote down the wrong thing. So this is 0.088. And so to get this lower value, what you're going to do is go 0.6 minus 0.088, and you get 0.512. And again, you do this for a two-sided test because you don't know which direction. Don't forget, you have to determine your alternative prior to collecting your data. So the goal of section 3 is to calculate that p-value. So what's the probability that our sample statistic is not 0.688? Because it's a two-sided test, we're actually going to be doubling our p-value since the normal curve's symmetric. So the probability, so this is the same thing as 2 times the probability that's greater than or equal to 0.688. And we're going to convert that to a test statistic, which is really your z-score. So our statistic is p hat, our mean is p, and the standard error we get from the formula sheet. And remember, when you're dealing with the null hypothesis, you're using plain p and plain q. We're going to substitute into the formula. So it's 0.688 minus 0.6 over the square root. Again, you're using p, 0.6, 0.4 over 125. And at this point, I would do the rest of the arithmetic with the calculator. So you're going into the calculator and you're doing menu, statistics, stat test, and you're doing a 1 proportion z-test. So our p sub 0 is actually what we're putting in our null, which is 0.6. And this is our evidence. There were 86 out of 125. And because it's a two-sided test, our alternate hypothesis is that middle one, the not equal, the default, because we don't know which way the test goes. And we see here that, let me just snip. Like the snippet tool, it saves time. So now this is going to be saving an enormous amount of time because I can just pull the information off, or it should save me time. Let me try to do this to shrink it so I can see what I'm doing. And our Z statistic, which you don't want to make sure you carry it out to at least 4 places, 2.0083. So what we're doing is, and I even want to shrink it some more. So what we're doing is we said, what's the probability that p hat is not equal to 0.688? That's the same thing as twice the probability p hat is greater than or equal to 0.688, which is the same thing as the probability that our test statistic, or actually, I almost made a mistake, 2 times the probability that our test statistic is greater than or equal to the value we just calculated, 2.0083. Our p-value you would get now by doubling the normal CDF. The low would be 0.688. Actually, that's not true. The low would be our Z value, our test statistic of 2.0083, 9E, 999, and then 0.1. So let's just check that out. So that would be menu, statistics, distributions, normal CDF. And so that would be the 2.0083, and that would be 9E999, and the default of 0.1. Now, the reason why it's not matching the p-value is I didn't double it, so we're going to have to double it. And if you see, it's almost, aside from rounding, it's pretty close. So our p-value is 0.0446. And I'm expecting you to calculate the p-value and write this up this way for the upcoming test. There's a method to my madness, and as we go through multiple choice questions, you'll understand my rationale. Okay. The next thing we do is we need to hit step 4. We have to determine, whether or not our results are significant. So we're actually comparing, this is my p-value, to our alpha of 0.05. And since the p-value is less than 0.05, we're going to reject HO. It's a very small chance of that happening, assuming the null hypothesis is true. And so therefore we reject HO. So how do we write this up? Let me erase this. You have to interpret the p-value. And I find that the picture that we drew on the prior slide is extremely useful. Sorry, this is taking a long time to write, to erase. Hold on. Okay, so let me just draw it out for you, because one of the ways that I like memorizing this interpretation is I like to have it make sense. So I'm just redrawing my little bell curve. So what I'm shading in yellow is the p-value. Or what we're calculating the probability of. So assuming 0.6 or HO is true, so p is equal to 0.6, there is a 0.0446 probability, that's my p-value, of getting a sample proportion of 0.688 or higher. So I'm just looking at the picture. Or a sample proportion of 0.512 or lower, purely by chance. That's the interpretation of p-value. And then you make your conclusion line. Since the p-value of 0.0446 is less than 0.05, we reject HO. There's convincing evidence that the DMV's claim is not true. Okay, now there actually is a part B of this question. It says construct and interpret a 95% confidence interval for the proportion of all teens in the state who pass their driver's test on the first attempt. Okay, so do you need to do every single step? Yes and no. You already stated the parameter and verified the conditions in part A. In step 1 and step 2. So you don't really need to do that, but you have to, you should state that. And now you want to write out the formula for the confidence interval. It's the statistic plus or minus the critical value times the standard error. Now for the standard error, you have to use the p-hat in the formula. That's one of the differences between the two formulas for confidence intervals and hypothesis testing. P-hat in this case was 0.688. For a 95% confidence interval, you can either recalculate it or just memorize it's 1.96. And then it would be 0.688. And let me quickly calculate 1 minus 0.688. That's 0.312 over 125. And then the rest, I would enter in the calculator to do the rest of the calculations. So you would do menu, statistics, confidence intervals, and we're doing a 1 proportion Z interval. And so that's 86 over 125, and it was for 95%. And now I'm just going to get my snippet just so it saves me some time since this video is probably a little on the long side. Shrink this. So the next thing you want to write down is the statistic plus or minus the margin of error. Well, here's the margin of error. So plus or minus the 0.0812. The lower limit is 0.6068 and the higher limit is 0.7692. And now we interpret. So I'm just going to erase the conclusion. We are 95% confident that the interval from 0.607 to 0.6769 captures the true proportion of teens who pass on the first time. Okay, this is an important sentence frame to memorize. A lot of times students are rewording it where it's not really the concept of the confidence interval. You're constructing this confidence interval, and 95% that confidence interval captures it, not the other way around. And then finally, the last part of the problem says, explain what the interval in part A tells you about the DMV's claim. So what is this interval? What information does this interval provide of 0.607 to 0.769 that the hypothesis test doesn't? What it does is it gives us the plausible values. And so when the claim, if you recall, that DMV was making was that the real proportion of students who pass on the first test is 60%. But we know that this interval is entirely above 60%, so that's a strong conclusion we can make. So since all the plausible values in the confidence interval are greater than 0.6, there's evidence that more teens passed on the first try than the DMV claimed. Okay, so that's consistent with rejecting HO, that the DMV underestimated the passing rate for the DMV. And we can see that based on the confidence interval as well.